Hello everybody and welcome to the online NPTEL certification course on semiconductor devices for next generation FETs, physics perspective. This is lecture number 12 and the topic of the lecture is capacitance modeling for high and low frequency part 2. For the body current, we have seen discussion from the previous lecture that the body current that you see, it depends on factors which are change in the bulk to source, change in the bulk to gate and change in the bulk to drain. So, if you look on the left hand side this figure, then there are 4 terminals: gate, source, bulk, and there will be a drain here. This is a drain here. Then this GGD is the resistance which you see is actually 1 by resistance everywhere. Please make it a point somewhere that GGD, if you want to find out, will be 1 over this, 1 over this and 1 over this, will give you the these are conductances, and therefore 1 over conductances will give you the resistance values at each and every point in this case. And what we see from all these discussions is that the variations or the values which you will get will depend on these resistances actually. Who defines these resistances? This is defined primarily by the doping concentration and the structural part of the device itself. If you take this signal here on the right hand side, if you take which comes out to be gate, source, drain and bulk, then you see G of GD is written here, gate to drain. This is bulk to drain, this is gate to drain, and then you have GS, gate to source, and you have then gate to bulk or bulk to source, this one. So, these 1, 2, 3, 4, right, and then the fifth one is basically between gate and bulk, right. Now, this if you take the of course the small signal for body leakage, then the body leakage component is given by this quantity which is GMX del VGB. Now, so this component GMX times del VGB will give you the value of the gate to bulk current. This will be primarily so this will be GMX, means basically you will have either GM or GMB coming into picture, either the material gate side or the bulk side. Now, let us take the complete small signal equivalent model for the intrinsic part only. We are not again we are not taking any extrinsic part, we are only taking the intrinsic part in the proper fashion, and with that we will do a complete low frequency modeling for that. Now, if you look at this figure here which is there in the intrinsic part, you see we have already taken into consideration this 1, 2, 3, 4 and this 5 that we have already shown to you in the previous slide, these slides. Then this is also taken the controlled source because of VGB, this also is done. These 4 components are there. Let us go one by one what is left here. This we have seen, this part we have seen earlier. Where we have seen it? In when we are doing the gate model. When we are doing the gate model, we did this part here, right, we did this part, and what is left therefore is the contacts itself. So, this contact, gate contact, source contact, drain contact and bulk contact, we have del Ig coming inside, right, we have del Id coming inside and del Ib. So, the convention which we follow is that the currents are always inside the black box. So, this small signal equivalent model which we are showing here, all the currents are all directed inwards, right, they are not directed outwards, they are directed inwards, and this is small signal for the equivalent part. That I will tell you why is it low frequency also. If you are aware of the fact that the capacitive reactance of any component is 1 by j omega c, right. Now, this is the capacitive reactance, right. Now, this is given by Xc equals to 1 by j omega c. So, when omegas are very low, Xc is very large, implying that these capacitor starts to behave like an open circuit, right, and therefore you do not see any capacitance sort of in this network. They are basically an open circuit, and therefore between any 2 terminal, if there would have been any capacitances, those are actually open circuit at low frequencies, and that is the reason you do not see any cap modeling here in the low frequency domain in this case, right, in this case there. Further, you will keep in also in mind that in most of the cases, for example, G of GB, for example, right, will be relatively very small value, right. Similarly, the which will be a big value will be basically your GM, and to an extent GMB, but you want GMB to be as small as possible. So, out of all these elements, you require GM to be as large as possible. That will ensure that your device is highly sensitive to variations in the input signal, right. So, this is what you get from the complete low frequency small signal model of the intrinsic part. So, we have done with small signal complete equivalent circuit of a model. Let me come to strong inversion and weak inversion case, each one of them individually, and see how the three terms which we have defined vary under the strong inversion and weak inversion. You will ask me why this varies. This varies because in strong inversion you are actually having an inversion layer being formed, right, and therefore that sort of screens the gate from the bulk, and therefore the influence of the bulk will be relatively small once strong inversion has been set in. However, that is not the case when weak inversion is there. Similarly, if you have a strong inversion and you want to find out, let us say, right, you want to find out drain conductance, then strong inversion drain conductance will be relatively low because your channels have been formed very easily and therefore the resistance will be small. But at weak inversion that is not the case, and therefore it varies. The gate, drain conductances, bulk conductances varies as you apply the bias and you move from linear non-linear to saturation, as well as from strong inversion to weak inversion to cutoff. Let us take up long channel device. So, we are doing a gradual channel approximation, and with that we know that my transconductance GM will be given as W by L mu times C ox prime VDS. What is mu? Mu is basically my mobility of the charge carriers, right, and at this stage we assume that the mobility is constant, right, again not a true one when you go to very short channel devices, and you assume that your VDS is less than the saturation value of voltage. Then my transconductance is W by L mu C ox prime by VGS. How do you define GM? GM was defined as del IDS del VGS. With respect to gate, when you differentiate, you will be only left with the drain to source voltage, remember, and therefore GM happens to be this much. When you go beyond VDS and you are into saturation, in this case saturation, when you are in saturation, then W by L mu into C ox prime into VDS prime comes into picture. And this is quite interesting, which means that transconductance in a long channel device is directly proportional to the applied VDS, be it in saturation or in the linear region. Now, why is it so? Because as the drain to source voltage goes on increasing, you are effectively having more and more current. So, the contribution of current becomes larger. So, the change in the current becomes larger, and that is the reason GM is larger. So, GM is del ID del VGS, right. So, rate of change of current with respect to VGS, right, and therefore, for a higher drain to source voltage, you would expect to see a larger change in the current because your transconductance has become larger in this case, both previous in the saturation, after saturation. Now, many books follow this basic one, which is this one, right, which is alpha is just a notational constant here, which we can give, and if you do a derivation of this one, you will get IDS equals to 1 by 2 W by L mu n C oxide. For n channel it is mu n C oxide prime. Oxide prime is basically meaning oxide capacitance per unit area multiplied by the overdrive voltage square, right, that is value of IDS which you get in saturation, please understand, right. So, the equivalent form, if you take generalized model, is this GM is equals to W by L mu n C oxide VGS minus VTH when VDS is greater than VDS and VDS is greater than VDS prime. These two are coming into picture, right. So, let me remove all the things from the slide. Another form of GM, equivalent form of GM, is given as 2 IDS by VGS minus VTH, right. This is 2 IDS, IDS is drain to source current and divided by overdrive, and that is for VDS greater than VDS prime in the saturation region. So, all these are in saturation region, and we see that this value comes out to be true. This is transconductance values which you get in strong inversion. Strong inversion is Vg much larger than the threshold voltage of the device. Let us look at the source to drain conductance GSD, right, and let us see how it depends upon the various factors. Basically GSD is the slope of IDVD. So, if you plot ID versus VD, right, drain to source voltage for a fixed VGS, then we define that to be as the small signal equivalent. So, if you want to find out the source, this is your IDS, this is your VDS, and you find the drain to source, and that is what you get. The variation of, so this is your del IDS and this is your del VDS. The division of del IDS by del VDS will give you the value of GSD, and it is given by this complicated formula looking formula here. So, do not worry from where I am getting it, but this is a formula which you get is W by L mu and C oxide prime VGS minus VDS, right, VSD minus flat band minus phi 0 minus gamma. Gamma is defined as the body factor, this is known as the body factor, and this comes from the fact that body factor, and this comes from the fact that if your source to bulk is 0, right, then this quantity goes to 0. If it is not, there will be a fixed quantity available here, and so on and so forth. This is for the linear region of operation which we get, right. Now, so you see, if you look at this formula which is shown here, as the flat band voltage or the drain to source voltage increases, your GSD actually starts to decrease, which is true also, because if you increase your VDS, you are basically having more and more current flow taking place. The rate of change of current will be larger, and that is the reason your GSD, which is del IDS del VDS, will become more, and that is the reason you have a negative sign here. Similarly, if you have more VGS, right, if you have more VGS, your more current will be there, and therefore your GSD will be higher. If it is more, there is a drain to source which you are applying VDS, and as you can see, as you make it larger and larger, right, when you make drain to source voltage larger and larger, GSD goes on becoming smaller and smaller, right, and as it goes on smaller and smaller, the 1 by GSD value increases. Why is it so? You think about it, why is it so? Increases, and a time will come when 1 by GSD will be approximately equal to infinity in saturation. So, this is the condition when you are in the linear region of operation, right, and that is the reason you see this is to be true. Now, there is another component which is under the square root. So, basically VDS plays a parabolic sort of nonlinear variation in the value of GSDs because of VDS. So, the simplified model of GDS will be given by this quantity here, it is VGS minus VTH minus alpha times VDS. So, as the VDS value again increases beyond a point, your GSD value goes on decreasing, right. This is your V overdrive which you see, this is your V overdrive, and it depends upon the various factors, but primarily on these two factors. Let me come to the next part, which is basically if you assume that there is a channel length modulation taking place. What is channel length modulation? Let me explain to you, and then I will come back to it. So, what happened was that when your channel lengths are very small and you have applied a drain bias here which is say positive in nature, since you are reverse biasing it, the depletion region will actually be more towards the drain side, and therefore, the channel will pinch off much earlier than your source. So, the channel will finish here, which means that your effective channel length was actually this much, right, but you ended up having your channel length to be only this much. This is known as channel length modulation, right. This is known as channel length modulation. Higher the value of VDS, more the shifting will be to the left, lesser will be the value of current, and therefore, its implication is that as you make it higher, the rather than, so this is without CLM and this will be with CLM. This is with CLM, if you plot VDS versus IDS, then this is with CLM and this is without CLM. Without CLM, you will see a straight line, resistance is maximum. With CLM, because of the reduction in the L, so as you go on increasing the value of VDS, since L is constantly going on lowering, so W by L is going on increasing, and that is the reason your current is increasing. and therefore you have a finite resistance even in the saturation region, right. So if you take CLM into consideration, you will get GSD to be approximately equals to IDS prime into 1 by L del LP by del IP, where LP is this distance, this is LP. So if, for example, if so you can see that it is inversely proportional to L, right, and as the L value goes on becoming larger and larger, your GSD falls down. GSD falls down basically means resistance increases, and that is true also. Larger channel, larger length channels will have a larger resistance. And how do you define LP is basically the distance between the pinch off region and the drain end. So how that length is varying with respect to VDS is very, very important, and that gives you a overall statement of GSD. This you need not be very much aware of at this stage, but typically we also have this expression of GSD as IDS prime divided by VA, which is a function of VSD, where VA is defined by this quantity, where VE is a constant value and VDS minus VDS prime is already known to you. VDS prime is saturation value and VDS is the actual value of drain to source voltage which you are given beyond the saturation. So this VDS minus VDS prime is the difference between the applied drain voltage and the saturated value of the drain voltage which you see here, correct. And this gives you a roughly a very good idea about the value of the GSD, source to drain conductance, which is known to us. Now with all these now being done, let us recapitulate everything on a single platform and see how does my GM, GMB and GSD vary, right. Now if you take first of all GM, that is the easiest one and the most critical one in terms of device understanding. GM actually shows a linear increase with the variation in the value of VDS, and then it becomes constant here beyond a particular value of VDS, which is expected also, right, because it is rate of change of voltage with respect to gate voltage, and it is given by this formula here, right. Let us look at GMB. GMB is what? GMB is the substrate transconductance, which is del IDS del VBS, and that gives you this variation here GMB, right, and it shows an increase with VDS and then again it becomes constant, exactly behaving like a GMB, but you see it is relatively much smaller as compared to GM, right, and therefore if you take this quantity GMB by GM, right, this should be actually much less than 1, which implies that my GM should be much larger as compared to my GMB, correct. So this is how my GMB varies with respect to VDS. If you look at GSD, source to drain conductance in general, then it actually with increasing VDS is first falls down, right, then around somewhere around saturation it becomes bare minimum, and then it becomes asymptotic with respect to VDS. So it is almost a linear fall till VDS prime, and beyond that it is almost getting, if you take the second order effects and if you take the simplified model, it is almost becoming asymptotic with respect to VDS, and this is true also. If you increase VDS value, your resistance go on changing, and that is the reason you see that your currents will be much more proficient changing as you change the value of VDS. So this one graph tells you where should you place your device if you want to use it as an amplifier, if you want to use it as a switch. If you want to use it as an amplifier, it is always advisable to place it somewhere here where transconductance is very large, so that for the same change in the input signal I get a larger change in the drain current. Similarly, if you want to operate at very low, or you want that your GM should be always higher as compared to GDS, again GMB, then you should also bias somewhere here. This will ensure that GM is much larger as compared to GMB. Very low values of VDS, more GMB and GM comes closer to each other. So it is advisable that you keep them very different and very far apart, and GM much larger as compared to GMB, GM value relatively larger as compared to GMB. Similarly, if you want to look at this particular point, then the maximum value of GSD will be when VDS equals to 0, and will be given as mu n C ox prime W by L VGS minus VTH you will get, right. So it is the first derivative for GSD which you will get. Now if you look at GSD and GM, GSD at VDS equals to 0 and GM at large values of VDS, their values are almost same, right, their effective values are almost the same. But since you do not operate at VDS equals to 0 any device, that does not make sense, the the GSD having a value of mu n Cox prime W by L into VGS minus VT does not make sense, right, and that gives you a brief idea or sense of this thing. Okay. We will discuss this weak inversion maybe in the next class, and what we have learned, let me recapitulate what we have learned. What we have learned till now is we have learned two important points here. The first important point I should tell you is that we are actually deriving the source to drain conductance, right, we did source to drain conductance in strong inversion. We also looked into the transconductance at strong inversion. We looked into the various formulas available to us for GM and GMB. We need to ensure that GMB by GM should be much smaller than 1, so that the gate has a much better control over the device. Lower the value of TOX, higher will be the control of GM over GMB, and lower will be the value of your GMB by GM ratio, right. So, this is one way of ensuring that the top gate has a better control as compared to the substrate is try to make your TOX as smaller as possible. Once you make your TOX as small as possible, you will be able to ensure that the top gate has a better control over the channel, right. And since anyway your substrate thickness is very large, GMB is very far away from the channel, and that is the reason its influence on the channel is very small, right. So, we have learned these things, and then we have also given you the equivalent small signal equivalent circuit model at low frequency for a MOSFET, right. This is a MOSFET which is very of relatively larger channel dimensions, and in this case if you see, you have an intrinsic only for the intrinsic part. In the intrinsic part, 3 terms, GM times VGS, GMB times VVS, and there was GDS term which was connecting between source and drain, and all the intrinsic parameters depending on the conductances are available depending upon the 2 terminals which are there, relative 2 terminals which are there in the device itself. So, with this let me close this class today. Thank you very much.